Greetings, Chem Fam. We are going to be going over percent yield today, which really is just a simple calculation. If you look right here, it is the actual mass from the lab, so the actual amount of quantity that we got after we did the experiment, divided by the expected mass from the lab, which is basically what we use stoichiometry to predict. So you're comparing what we actually got in the lab versus what stoichiometry in a perfect world would predict you'd get out of a reaction. So let's look into how we can actually do that. There are a few steps to take. Step one would be to read the problem and start to figure out if we can get a balanced equation. So let's see, it says determine the percent yield for a reaction between 46.5 grams of zinc sulfide and 13.3 grams of oxygen if 18.4 grams of zinc oxide is recovered. So first of all, that's saying that 18.4 grams of zinc oxide is the actual mass from the lab. All right? So let's make sure that we note that. That's the actual mass. That eventually we will use to plug in to our equation for percent yield. But before we can do that, we've got to figure out the expected mass from math, which means we're going to have to do some limiting reactant style problem. Okay, so we know that zinc sulfide is going to react with oxygen. And we know oxygen by itself is O2 because of Brinkelhoff. It's a diatomic molecule. Now we know that zinc oxide is going to be recovered, so that must be one of the products. And it says it's also recovered alongside an unknown quantity of sulfur dioxide. Sulfur 1, dioxide 2 oxygens. Okay, so now that I have that, you know the drill. We need to balance that due to the conservation of matter. And let's see, how would we do that? Well, we have one zinc on this side and one zinc on that side, one sulfur on this side and one sulfur on that side. But we actually have, three oxygens on this side versus two. So I think we're going to have to make this one oxygen over here a non-odd number, so an even number. So let's put a 2 there and see what happens. If I do that, it's going to make 2 zinc, 1 oxygen. All right. If I put 2 here to make it 2 zinc, now I have 2 sulfurs. So now I have to put that there to make 2 sulfurs. Wow, in the end, how many oxygen do I have? 2 plus 4 gives me 6. So I'm going to have to put a 3 there. Oh, that was a good one. That was a trickier one than normal. That's a 2:3:2:2 ratio. And again, I'm going to double check that just to make sure that's okay. All right, looking back at it, everything does seem to be totally balanced out, so we're good there. Now that we have a balanced equation, let's work on finding our limiting reactant. Why? Because we need to know which reactant runs out first so that we can predict the proper amount of product. Once we know the proper amount of product from the limiting reactant, that's when we can get our expected mass from stoichiometry. So let's go ahead and do that. I have 46.5 grams of zinc sulfide, and I also have 13.3 grams of oxygen. All right, we know that we're going to need to do a mass-to-mass conversion, which means that these are 3-steppers. Why? Because we need to go from mass of A to mass of B to figure out how much is the actual expected mass. Now, since we know we ended up with 18.4 grams of zinc oxide, we need to solve for theoretically how much zinc oxide would be formed. So that's what we're looking for in the end, is a little zinc oxide. So we will put that in there. We know we're searching for the grams. So let's do that. Okay? Now it just becomes straightforward 2 stoichiometry problems to go from mass of A to mass of B. So to do that, first I'm going to divide by the molar mass of zinc sulfide, which is 97.46 grams of zinc sulfide for every 1 mole of zinc sulfide, right? Just following my mole map. Next, I'm going to go from get rid of moles of A and go to moles of B. A moles is what we started with. In that case, it's zinc sulfide, so there's 2 moles of zinc sulfide. And B is what we're looking for, which is over here, zinc oxide. So that's 2 moles of zinc oxide according to the balanced equation. Let's write zinc oxide in there. ZnO. Okay. Now that we're doing that, we're going to get rid of moles of zinc oxide and multiply it by its molar mass, which in this case, when you add up on the periodic table, is 81.39 grams of zinc oxide. How do we figure that out? We took 1 zinc plus 1 oxygen off the periodic table. Now, when I calculate all that through, which, by the way, make sure my math works out with my units, moles cancel, moles of ZnO, good. Everything looks good there. It looks like my answer comes out to be about 38.83 grams. Now, this number doesn't have any meaning really to us yet until we start to determine how many grams of zinc oxide would form if we used up all oxygen. When we know which one produces the least amount, then we know which is the limiting reactant, which will tell us how much of the product will actually be formed according to the math. So let's do that. If I'm going to end up converting my oxygen into moles, I need to divide by the mass of 2 oxygens, which is 32 grams of oxygen. When I'm converting now, I am going to do my mole to mole ratio, A on the bottom, B on top. My A right now is my oxygen, so that's right here. There's 3 moles of oxygen for every, according to my balanced equation still, 2 moles of zinc oxide. And oops, I forgot to write moles in there. Let me put that above real small. Sorry about that, a little sloppy there. And now I want to get rid of my moles of zinc oxide, and I want to turn that into the mass of zinc oxide. In this case, we know from earlier up above, it's 81.39 grams of zinc oxide for every mole of zinc oxide. Now, if I calculate that out, remember, multiply the top, divide by the bottom, I end up getting about 22.55 grams. 22.55 grams. All right, so now here's the big reasoning. Since oxygen creates the smallest amount of zinc oxide, this tells us that oxygen is our limiting reactant. Now, since oxygen created the lowest amount, that means that this becomes our mass from math, right? So this is what we predict from our math. So now that we know that when doing this experiment, we should expect 22.55 grams of zinc oxide, we can compare that to the 18.4 grams of zinc oxide. So let's do that real quick. Percent yield, if you look up at the top left, the equation for that is actual mass divided by expected mass. So my actual mass, which was given to me in the problem, was 18.4 grams. My expected mass, and it's expected because it's from the math, the stoichiometry, we expect 22.55 grams of zinc oxide. So if we divide that both and multiply by 100, we end up getting a total, which is 81.6% yield. What does that mean? It means that we got about 81% of the zinc oxide out that we expected. Now, what happened to the other 20% or so? Well, a lot of things could have happened. We could have lost it in a beaker when we poured it and filtered it out. Some could have still been stuck in the beaker. We maybe didn't measure out exactly these amounts, like 13.3 grams of oxygen in the beginning. So therefore, there could have been some error involved with that. But for some reason, the reaction, you didn't get everything fully reacted to get your expected 22.55 grams. In this case, you only had 81.6%. But that is called the percent yield because that's how much you got out versus what was expected. Just like on a test, if you end up getting an 88% on the test, that means you're expected to hopefully get 100%, all of them, but you got 88% of that, and that's why you get that grade. Same thing with percent yield. You're expected to get all of those grams out, but things happen in chemistry. They don't always go, reactions don't always go all the way finished. So, therefore, you only had 81% this time. Hopefully that shed some light on things for you guys. Of course, you had to first balance your equation. Then you had to find the limiting reactant. Once you did that, that allowed you to predict the final product from the math, and you compared that final product from the math to what you actually got in the lab. And when you take actual divided by the mathematical estimate, you end up getting your percent yield, which is basically like a grade. How well did your experiment go? All right, ChemFam, hope this makes some sense to you and that you see the relationships between what we've been learning and how it can apply to figuring out the percent yield. You guys have a great one. Thanks for listening.